Hello, in this video I am going to go over Kirchhoff's laws and how they can be used in conjunction with Ohm's law and others circuit analysis techniques to analyze electrical circuits. So first, before I get into that, I'm going to review how electrical circuits are usually presented. So they're usually drawn as schematics, which represent components with certain symbols that make it easier to read circuits. And so we have some symbols here. Common symbols include, uh, so we can have a symbol for a cell, which looks like this. So the positive end, there's going to be two parallel lines. One is longer, one is shorter, and the positive side is going to be the longer side. And this is a cell that can provide a voltage. And then you can also have usually when you have a battery, this could also be a battery as in a cell. But when you have a battery made up of multiple cells, you can usually draw that as two of these cells like this together. And again, the positive side is on the longer end. And then this is a multi-cell source, the voltage source. Now, something about both of these, also, you may also see, sorry, I'll add one more. You may also see a voltage source look like this. So this is a circle, um, with a positive and a negative end. Then this is also just a voltage source. Something about these three are they are constant voltage sources. So what this means is that they always have a constant voltage across their two terminals, regardless of what happens with the rest of the circuit. So the voltage across the two terminals of any of these does not change. So like let's just say the cell was a 3-volt cell, then there will always be 3 volts across the cell. And that's what it means by constant voltage, is that the voltage across them remains constant regardless of the current going through them. Now you may also see things like current sources. So like if this is a voltage source, then a current source will usually just look like a circle with an arrow inside. And then this is a constant current source. Uh, and then this is almost like a battery, except a constant current source always has a constant current through it. Um, which means that regardless of what the rest of the circuit is, this branch of the circuit with a constant current source will always have a constant current. So like if there was 1 amp, if this was 1 amp constant current source, then this branch will always have 1 amp flowing through it, regardless of what the rest of the circuit looks like. So the voltage across this constant current source can change, but the current stays the same. Whereas for constant voltage sources, the voltage across them stays constant while the current can change through them. Now, some other components that you might see include a resistor, which looks like the zigzag thing. So this is a resistor. And this will be an ohmic resistor, which means that it follows Ohm's law and is linear. Now, you can also have things called potentiometers or variable resistors, and that looks like a resistor with an arrow going into the middle of it. And so these two, so this is a potentiometer or a variable resistor, and what that means is the terminals, so across this is a constant resistance. So like if I label this A, B, and C, AC is just a normal resistor, so that's a resistor. But then AB and BC can vary, so these are variable. The resistance across these 2 points is constant. Let me rewrite this. So resistance across AC is constant. Um, but resistance across AB and resistance between B and C are variable. But they follow the condition that AB plus BC is equal to AB. I mean AC. So that's a potentiometer. Um, now, let's see, what else is it? There's also um, capacitors, which usually just look like two parallel plates of the same size. So a battery or a cell would be two plates of different sizes, but a capacitor um, has two plates of the same size. And now capacitors, sometimes they can be drawn like two curved plates, I think, or you can have a curved plate and a straight plate, and that would be a polarized capacitor, which means that the straight part is positive. So the voltage across it always has to be that there's a positive voltage on the positive terminal and negative one on the, or the voltage difference has to be positive going from negative to positive. And so those are like some capacitors have a polarity, which means you can only put them in one direction. And so that's what that might look like on here. So these are all capacitors though. So this is also a capacitor, and then this is a polarized capacitor. So cap, and then cap. Um, Now there's also some circuit components such as really basic, a line here. This is just a wire. So whenever you just see a line, that represents a wire. And whenever you see lines connected like this, usually they'll be connected through like there'll be a little dot there. That will be when there's a dot here connecting at the intersection of lines, this is a junction. So this just means that the wires are connected at that point. Whenever the wires aren't connected and they cross, usually you'll see them as like that. So where there's a bump on it, this means that the wires are not connected. Um, Now, you can also have things like switches. So a switch might look like, depending on what type of switch it is, it might look like this, which is just a simple, this is just the most simple switch you can get. So this is the switch in the open configuration, and when it's closed, it'll just look something like this, so like a wire. So this is open and closed. And then sometimes you can have switches with like more than one terminal, so like it'll look something like this. Uh, where like the switch can alternate between two different wires here like that. But these are all different types of, so this is also a switch. But this is different types of switch. And then there are many different types of switches, but the most simple one is just this, where it's like a lever, and then it can either be open or closed. But you can usually tell what a switch is doing just by looking at how it's connected. So like if it's open, it's not going to be connected, and if it's connected to one of the, like you can just see the connection as if it was a wire and junctions. Finally, we might see some semiconductor devices. So these are like, for example, a diode will look something like this. So a triangle with a line, and then this is a diode. And a diode, current always has to flow in this direction in an ideal diode. So a diode only allows current to flow in one direction, and it's in the direction of the triangle, basically. And then you have some special diodes, LEDs, called light emitting diodes, um, that emit light when current passes through, or when the when a current passes through them, and those will look something like a diode with a circle around it, and then some arrows coming off of it to represent that it emits light. So this is an LED or a light emitting diode. And again, these two devices here, they are semiconductors. There's also like transistors, but those are more complicated and outside the scope of this video. So semiconductors, which means that they are not linear. so they don't follow Ohm's law. Um, but even so, that means that you usually a lot of the circuit analysis techniques that you use cannot be applied to semiconductors. Like you can't use Ohm's law on a semiconductor, um, because it's not ohmic and it's not linear. But semiconductors are very useful for certain purposes, especially in more complex circuits. Okay, so now that I've reviewed schematics, so what a circuit might look like, I was already using these symbols would be like, you might have like a battery here. Um, so like this is an example circuit. Like you would have a battery here, and let's just say that's like a 1 point, or I don't know, let's say this is like a 9-volt battery. And then you might have the battery connected to like a resistor. So this would be like a resistor in series, and then you could have it like go off into like two different branches with like capacitor in one of them, with a switch, and then like another branch here would be like I don't know, like an LED. So there's like circuit these circuit symbols are just a like a blueprint for how you would draw circuits, real life circuits, while making it easy to read. And so usually these will also have values assigned to them. Like this would be like, I don't know, maybe let's say 100 ohms, and then this might be like 100 microfarads, and then this LED would be like, I don't know, 3.3 volts or something. So usually these are labeled and have values assigned to them. And a label might look like, I don't know, like V1 or battery one. And then this might be like R1, C1, and then LED1 or D1 for diode. So that's what a circuit might look like. And obviously they get way more complex than that. Now I'm going to go over Kirchhoff's laws, and these are essential for circuit analysis. Now, Kirchhoff's laws are basically built on conservation laws, so like conservation of charge or energy. Now, the first one we are going to review is called um, Kirchhoff's current law. So Kirchhoff's circuit laws refer to two laws governing how circuits work. So there's Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law, usually abbreviated just KCL, and also called the junction rule. So Kirchhoff's junction rule. That applies at junctions we defined. So a junction, really you can say any part of a wire is a junction, but usually when you do junctions, it's like when you have a node here and then you have multiple wires extending into it. What the junction rule says is that if you have currents here, so like I1, I2, and I3, the sum of the currents going into a junction or out of a junction, so the sum of the currents at the junction is equal to 0. And what does that mean? And this is a signed sum. So like if we're analyzing the currents going into a junction, we have I1 plus I2. So these are positive since they're going into the junction, minus I3. And I3 is negative because it's coming out of the junction, is equal to 0 for this example. So this is an example for that. But basically, all the currents into and out of a junction, summed with their signs, is equal to 0. And this follows the conservation of charge, because basically all the charge that comes in and out of a junction have to be equal to 0, because no charge gets created or destroyed at a junction. So that means that at the junction, there has to be 0 net charge coming in or out of it. So the current into a junction equals 0, and the current out of a junction equals 0. The sum of them. So like I said, the sign just depends on whether you're going in or out. So like this is the current into a junction. If I want to see the current out of a junction, which is also equal to 0, it'd just be negative I1 since it's going inwards and we're analyzing current going outwards, minus I2 plus I3. It doesn't matter what you use because again, both are equal to 0. But it just you have to be consistent with the signs. So like if you're analyzing current into a junction, you need to make sure that all the currents going inward into the junction are positive and all the currents going outward are negative. And now this has one really easy to see implication, and that is for a series circuit. So a series circuit describes when components are connected like in line like this. So like this is a series circuit with two resistors. And now what that says about a series circuit is that the current through a series branch circuit is constant. So if you have like multiple resistors here, the current through this first resistor, so let's say R1 and R2, current through the first resistor and the current through the second resistor are equal. So I1 equals I2. And why is that the case? Well, I said, a junction can really be any part of a wire. So let's say that there's a junction right here. Now at that junction, we have two wires connected to it, basically. You can say and then there's I1 going into the junction and I2 going out of the junction. So now if we sum that, we get I1 into the junction minus I2 because it's going out of the junction is equal to 0. So I1 equals I2. And so this means that the current throughout any series branch is always going to be the same throughout that branch. So that follows from Kirchhoff's current law, or KCL. Now we will get into Kirchhoff's voltage law. So Kirchhoff's voltage law called KVL, abbreviated, or known as Kirchhoff's loop rule, states that for a closed loop, so it has to be a closed loop. So again, for a closed loop in a circuit, the sum of the signed voltages is equal to 0. And so before I said this follows from conservation of charge, Kirchhoff's voltage law. Current law. So this can be seen as conservation of charge. Kirchhoff's voltage law can be seen as conservation of energy. So remember, voltage is equal to energy per charge. So change in voltage is also, or change in voltage is also change in energy per charge. But what this means is that for any closed loop, the sum of energy has to be equals to 0. So energy is conserved. And so what does a closed loop look like? Well, let's just say we have a battery and like a resistor here. A closed loop is just like that would be a closed loop. So the battery and the resistor. Or if you have like, I don't know, if a more complex circuit, like maybe you have a battery and then you have multiple resistors. And then, so like going into a network, like, I don't know, like something like this maybe. Or here, let's draw another resistor here. So what Kirchhoff's voltage law, or KVL, says that for any loop you can draw, like this loop here, or this loop, or this loop, or you can draw like a loop around this whole circuit, or you can draw a loop around like these two parts here. any of these loops, the voltage, the summed voltage is going to be equal to 0. Now, let's think about why this is true. So if you have a loop here, the voltage has to be equal to 0, the sum voltage, because, like, let's just say this is a 3-volt battery. Let me do this in a different color. And then this is a resistor. The resistor also has to have 3 volts across it, but the resistor has 3 volts in the opposite direction. So when we're going in the loop, we have to remember, so this is signed voltage, which means that you have to pay attention to whether voltage is increasing or decreasing as you go in the loop. So like for this one here, Kirchhoff's voltage law, KVL, states that the sum of the voltage sign. So like if we follow the loop counterclockwise, we see that the voltage here decreases by 3 volts as you go past the battery, because it goes from positive 3 volts to 0 volts, or the negative side. So that's negative 3 from the battery plus 3 volts across the resistor, because you're going from positive or 0 volts to positive 3 volts on the other side of the resistor, is equal to 0. So you have to pay attention to signs. So like, let's just say I have another circuit here that might look like, let's see, maybe we have like 2 batteries here. So like one battery that looks like this and one battery that looks like this in opposite directions. And then there's a resistor going through them. And then let's just call this battery here V1, V2, and then VR. So what Kirchhoff's voltage law says, if we choose a loop in here, and it doesn't have to be clockwise or counterclockwise, you can just choose one. Because it equals 0, it's going to be the same. Let's just go counterclockwise here. We know that this is positive and this is positive, negative, negative. Now, from this, we can see that since we're going positive to negative, the voltage is decreasing. So that means V1 is negative. So we have negative V1 plus, for V2, we're going negative positive, so voltage is increasing. So we have positive V2 plus VR is equal to 0. And VR, we don't know what it is, but we can just call it positive for now. And if VR turns out to be negative, then we know that voltage is actually decreasing going across this, going counterclockwise in this loop. So if V is positive, or really, you can say that V1 is positive too, but if you calculate it, V1 will be a negative value. So if this battery is like if the battery has like 3 volts, so if the battery is a 3-volt battery, then V1 would be equal to negative 3, because it's going backwards. So when I say like, you have to be careful though what you're referring to. So if you're just using variables, you can all set them all positive, but the values can be negative or positive. But like if you just want to use positive values here, V1 would be negative 3 volts here, plus V2, like let's just say if V2 was 2 volts, then this would be plus 2 volts, because the battery is in the same direction as V2, or the loop. But basically, like, depending on how you label it and how you do everything, it just has to be, the sign voltage has to be equal to 0 as you go across a loop. So again, so like if VR turns out to be negative, like let's just say VR is negative 1 volt, then that means that this side is 1 volt higher than this side. So since we're going across, like in the direction of the loop, is the sign of this voltage. So if the sign is negative, then your voltage is decreasing as you go along the loop. And if the sign is positive, then the voltage is increasing as you go along the loop. And the sum of those increases and decreases in voltage is equal to 0. Now again, let's think about why this makes sense. So let's just say you start at a point in a circuit. So I'll just draw, like, let's just say you start at a point in a circuit, and then let's just say you start at 0 volts. If you return to that point after going through a loop, you should still be at 0 volts because it follows Kirchhoff's voltage law. Now let's just say something. What does it mean if it doesn't follow? Like, what would that look like if it doesn't follow Kirchhoff's voltage law? Well, it would mean that if you start at 0 volts and you go through the loop, you get something that's not 0 volts. So you'd be like at 1 volt after going through the loop once, or -1. And then if you go through the loop again, you'd be at like 2 volts. And then so that just what that would mean is that as you go through loops, the voltage would keep on increasing. And since voltage is equal to energy over charge, that would mean energy would just be increasing um, through a loop, which makes no sense because a loop is a closed system, because it's a closed loop. So that means the energy has to remain the same after going through the loop at all times. So that voltage cannot change going through after you make a round through the loop, which is why the sum of the sine voltages, so the voltage increases and decreases, have to be 0. So again, by sine voltage, I mean if voltage decreases in the direction of the loop, it's negative. And if voltage increases in the direction of the loop, it's positive. And if you don't know what a voltage is, you can set a variable to it, and the variable could either be positive or negative. Now let's look at one something that comes out of voltage, Kirchhoff's voltage law, that is really useful. So and this is for parallel circuits. So before in KCL, Kirchhoff's current law, we saw that for series circuit, the current is the same. Well, for parallel circuits, following KVL, we can say that the voltage across any parallel circuit branch is also, across parallel circuit branches is the same. So we have like V1 and V2. So these are the voltage drops, and this is the V battery here. I'll call it VB. Or that really, so what Kirchhoff's voltage law states is that, or what we can deduce based on Kirchhoff's voltage law is that V1 equals V2 equals VB. And now why is that true? Because from Kirchhoff's voltage law, if we draw a loop like this, we get that since we get V1 plus VB is equal to 0. And let's just assume VB is positive, then that just means okay, these are absolute values really, it should be, but okay. So if we say V1 is the drop across the resistor, then V1 would be negative in this equation because it's a drop, and VB would be positive because it's a rise going in this loop. So we get VB is equal to V1, or V1, if we define V1 as the drop across this resistor, and that's what basically we're saying here. V2 here, if we define it as the drop across the resistor, we get that, because we can draw another loop that looks like this, with just VB and V2. We get that VB plus negative V2, because V2 is a drop, is equal to 0. So we get VB is equal to V2. And basically, for any branches in parallel, from using Kirchhoff's voltage law, we can see that the voltage across the parallel branches is going to be the same. And so that's a really important conclusion following from Kirchhoff's voltage law. And we can use these laws to analyze circuits. So I'll do one really simple example circuit using Kirchhoff's laws and Ohm's law to analyze what is going on in the circuit. And you can use these principles for much more complex circuits too. But for example, let's just say we have a circuit here with a battery. So this is a 9-volt battery. And then we have a branch with a resistor here. So this is like a 3 ohm resistor. And then we have another branch here with 2 resistors. So this is a 1 ohm and 2 ohm resistor. Now, from Kirchhoff's laws, and like we said before, the current through this branch has to be the same So this and the current through this and the voltage is from both these rails has to be the same. So that means that the voltage across this resistor here has to be 9 volts because that's the same as the battery, and these are parallel rails. So the battery is 9 volts, so that means that this resistor also has 9 volts through it. So if we call this R1, R2, and R3 here, or actually I'll label them so they match the resistance. So this would be R1, R2, and R3. We know that the voltage across R3 is going to be 3 volts, and the resistance of R3 is 3 ohms. So by Ohm's law, we get that the current through R3, so let's just call this I1 and I2. So we get I2 here is going to be equal to voltage, which is 3 volts, divided by resistance, 3 ohms. So that means that there is 1 amp of current going through this branch in this direction. Now for the second one, by series resistors, so when resistors are in series, you just add them together because I'll go over this really fast, but and I'll cover this in more detail in another later video. But you know, resistance is equal to row length over area. So if you add them in series, you're essentially adding the lengths. And so you would just add them together because the length increases. So resistance here, if they're in series, you are going to add the resistances. So let's see. The equivalent resistance of this branch is going to be R1 plus R2 equals 3 ohms. And like this branch, we already did the calculation. That means that since there's 3 volts across this branch from Kirchhoff's voltage law, we know that the current across the branch is going to be equal to, by Ohm's law, this should be, I misread it. This should be a 9 volts right here and a 3 amps because there's 9 volts across this and then 3 amps. So I2 is 3 amps. And then I1 is also going to be 9 volts because it's in parallel with a battery. And then there's going to be equivalent resistance of 3 ohms. So there's 3 amps. Now, there's 3 amps going down this branch, which means that we know that for each resistor, there's 3 amps going through it because of Kirchhoff's current law stating that the current has to be the same. As we saw, it's a consequence that the current is the same through a series circuit. So both of these resistors have 3 amps going through them. And so what we can see from that is, using Ohm's law again, we know that the voltage across R1 is going to be equal to 3 amps times 1 ohm. So that means that there's a 3 volt drop across R1, and then R2 is equal to 3 amps again because of series current times 2 ohms. So that means that there's a 6 volt drop across R2. And this makes sense because when you add those together, that's 9 volts, which is equal to the battery voltage. So that's a really simple example of how you can apply Kirchhoff's laws and Ohm's laws to analyze a circuit.